Remember every time. Okay, now I'm gonna hand something down for those of you who are here in the room, but everyone else I can show you the canvas. What feels weird is handing things out anymore because everything is all online. Syllabus, and then we also have the schedule.
Do you have a, what's it called? What is it called? A hole puncher in the room?
I don't, but there is one in the department main office.
The one that's locked or the other side?
I guess it often is locked. I'll hook you up.
Okay, thank you.
Now, and for those of you who are online, here's the main page in Canvas. So what I just handed out today was the syllabus. Oh, I also need to put up a link here for the schedule. But it is in Canvas, but okay. Let me take care of that right now. Good thing that I'm not really under serious pressure to get to a certain point by today, because it would definitely not be happening.
Guess what I don't have to do this semester?
Oh, what's that?
I don't have to join online. I got classes.
Oh, great. Oh, that's why you weren't.
Mm-hmm.
Cool. Okay, so what is that? Sorry, it's gonna drive me nuts. I have to fix this. There's some blank link in there somewhere. And that's just intolerable. Okay. Sorry, this is this. Okay. All right, there's the syllabus link. Okay. And then there's the. Oh, okay, yeah, apparently there's another link here that's. Yeah. Technical difficulties. Okay, here. Syllabus schedule over two things that I handed out. So yeah, we go ahead and and since the cold weather we've had did not influence those who schedule things at all, which is not surprising. Unless there's some sort of tornado or hurricane later, I expect we'll be able to stick to the schedule that I do see here. It takes into account the various breaks that we have, March break, spring break, and so forth. Okay, now, let's see, I'll go through.
LOL. For the midterm, you put Fab 26.
What I put?
Fab 26 instead of February.
Oh, okay, hold on. Oh, Fab instead of Feb. Okay. Oh, kill me now.
It's one of the mornings.
Yeah. So, dang it. And well, I do want to talk about all that in a moment. Anyway. Also.
Will we do a project in here?
Yeah, I'll talk about that momentarily. Okay. All right, so now that I've at least fixed this in Canvas, okay. I don't like this small preview window. I just want to see. actual syllabus. Oh, okay, can make it. Okay. Um, because later today I had my other class, Cal 3, which, oh yeah, you two were in a year ago, so I get to do that all over again.
Yes.
Not really. So hopefully get all the things kinked out in this class, where it's only a few days. So, okay, but no, I can't do the whole like, oh, if I'm aware if something's wrong and like, oh, I can't fix it, I gotta fix it now. Okay. I think we will reset button today. Now, of course, you all were in Math 465, 60. Well, not everybody was in that last semester, but had all taken it at some point. So this is meant to be a continuation. So the focus is going to be at first numerical linear algebra. So solving systems of linear equations by either direct or iterative methods. After that, the rest of the semester is spent on solving numerical systems of ordinary differential equations, starting with the initial value problems, the time-dependent problems, and then 2-point boundary layer problems. As part of that, last semester you saw how to solve a single nonlinear equation using methods like Newton's method or fixed point iteration. After seeing the numerical linear algebra stuff, we'll be able to solve systems of nonlinear equations as well as linear, and that'll play a role in solving differential equations. Okay, so still using the same book, just different chapters in it. Of course, there'll be a good chunk of MATLAB. My website that I've had for all these years that has all my classes, of course, the powers that be over at iTech took it down last semester, and for the time being, I've replicated it over here at this address. It's rather non-intuitive, I've actually bought the domain proflamberts.org, but I haven't been able to do anything with it yet. But for now, you have everything in Canvas, but we also have this that has a lot of resources. I've not yet determined my office hours. Well, I do for sure have office hours on Tuesdays from 2 to 4. I may have other office hours. I'm still getting the rest of my schedules for that, but I'll make an announcement about that once I know. Okay. You all have the book. So we'll be looking at chapters 3, 5, 11, 12, and 13 this time around. Okay. Now, as far as coursework, some things will be similar. You'll have the same kind of homeworks, the explorations, and you'll have the Canvas quizzes. There will be a midterm that's similar in format to what we had for the midterm and final last time. And since 40% of the students in this class are taking it online, so the midterm will be in a take-home format as well. But I do not want to have a debacle like I did with the final last time. No one here was involved in that, but there were clear instances of collaboration when collaboration was wrong. When you have work that is very wrong and very similar between students, it stands out, and I'm just going to give an accept if that happens. And since 60% of students in this class are graduate students, the accept is bad anyway, but for grad students, it means you're kicked out. So it's not worth it. Take the point loss. Okay, the final, however, will be very different. Just because for material differential equations, I never felt good about the kind of questions I might ask you on in-class test. So here are the options. Option number one, comprehensive oral final exam. That means we hold a meeting, you know, it could be in my office or it could be over Teams, you know, for 45 minutes to an hour or so. And I get to ask you about any of the topics. I would not get to MATLAB, that's not something that can be done in that kind of format. But for example, about the different methods that we're going to see, what are her properties, what are her advantages, what are her drawbacks, things like that. I'll be able to say more as it gets closer, but that's one option. I think we've already ended up taking that one because the other option is quite a coding project, and I think I'll check if information about it is already posted in Canvas. But what you're doing is you're implementing various methods for solving the last kind of problems that we'll consider this semester, 2-point boundary value problems. So implementing like, you know, shooting methods or finite difference methods in MATLAB, and then comparing their performance and so forth. Yes.
So for the first one, would it just be like us studying from like the notes from what we learned, or would there be like a list of specific topics?
Okay. Well, yes, we'll be studying from the notes and so forth. That's your best preparation. I can give some examples of the kind of things that I would ask about. Yeah.
Okay.
Or you can do a coding one. So each of you can make that individual choice. And at least since there's only 5 of you in total, it's pretty easy to make it all work. Okay. Here's what everything counts for. So mainly the exams. Okay. There's all the stuff that the university makes me put in syllabus. Yep, so I'll call this section. New section on AI. I have had a couple instances, not really for a class, but for research, of my students trying to use things like ChatGPT to help them with various things. And I found that when it comes to this level math, AI does not bring the I. It's very much the A. So actually, I've had the using experience of like going to ChatGPT and I could like since it's a language model, so I can ask it to ask the information about my advisor because he was really famous, and it put out a semi-correct biography of him, and then I got to do the same for me. Like it known my interest in partial differential equations and so forth, but it thought I went to Berkeley, not Stanford, and got the year wrong. And certain other details. I think ChatGPT is like a slacker student. Like it creates the appearance that it's really trying, but this is just getting everything wrong. It's sloppy and it's trying to get by. So yeah, that's what we want to have take over the world. But we have Skynet. So okay, so that's all the syllabus stuff. So any questions about? Yes.
So about the options for the final.
Yeah.
So the coding project.
Yeah.
Now, is it something you start working on, like you work on it throughout the semester, or it's something that's happening closer to the end?
Okay. Actually, let's see what I have a bit. Even if I haven't posted it for you all to see in Canvas, let's see what. Okay, yeah, as far as material that I do have. Oh yeah, so for a midterm, there's information about that available already. So then we start preparation for that very soon. Okay, as far as assignments, okay, so I haven't published assignments in here, but I think I have the info here. Oh, I do. Great. All right, so I can show you. I mean, I'm gonna make 20 changes, but. So this I give you the gist, okay. I'll do that. But yeah. Oh, yes. Obviously, certain details have to be changed here. So for example, but yeah, this information I can make available to you at any time. Now, you might have difficulty implementing these things because this deals with the last topic of the semester of 2.5 writing poems. So if you want to get a head start on it, you got to read ahead. I know, but certain among you are not above doing that. So, but yeah, it's like ready function just form to solve this problem and so forth. It's all here to and I've included code that will handle the testing for you. Like the code is defined. Here's the sample 2-point vector value problem. Run it for a certain number of grid points. Here's the error. It'll plot the solutions for you, so you can see if they agree. So there's a lot of the testing infrastructure is there for you. And then shooting method and variations using a secant method or Newton's method. That's it.
100 and 200 points. Oh my gosh.
Oh.
And
yeah, that doesn't take that long though. So
yeah.
Okay. This is it's not like your method, but yeah. Okay. Okay. So anyway, and I have the skeleton, like the code for testing, and then these are functions you write. So I just have like a skeleton at the start that has some comments and things to refer to in the text and so forth to help you get the ball rolling. So, yeah, you can try that on. So. Okay. All right. Okay. Any other questions about the class itself?
So timing wise, so the final project is, it depends, I guess, on the option you choose for the final.
Yeah.
So if it's an oral exam, like when dates?
Yeah, okay, so because classes end May 1st. For the last class day that we have is set aside for if anyone is doing a coding project, I'll be talking about that, taking questions on that. So the material will be covered. Okay, so I'll finish covering material like at the very end of April. So then you have a whole last week of classes and then all finals week. I figured people will be, so during the last week and a half or so is when you'd either be scheduling and getting the oral out of the way if you're doing that, or working on the code. And I want to have everything finished by the end of finals week.
Yay!
Yeah. Okay.
Oh, we have a concept due next week?
Right, yeah, because Monday is when I finish covering the first section.
Okay.
Although I'm gonna feel the same way about 2 days this semester as last. Last semester, I did a fair amount of homework dropped on me at the end. It wasn't so bad though. And now we're only 5 of you, so.
It can't be too terrible.
Yeah, so not to worry about it. Let's see. Oh, also for the homeworks, okay, there are a grand total of 9 regular homeworks, and the lowest 2 get dropped out of 9. And okay. There are no lowest quizzes dropped. You got to do no quizzes. But the quizzes are only 10%. There was a mix-up last semester regarding the homework and quizzes. Because I wanted the homeworks and quizzes to count equally with each other. But because the homework starts at 100 points, the quizzes would be like, up to 14 points or so. You end up weighing the homeworks a lot more. But this is fixed this time. They're in separate categories. So the quizzes are 10%, each quiz counts equally. So there are 8 quizzes, and then the homework's of our own category is 20%.
And we have to complete all of the quizzes.
Yes, you do. Well, I mean, honestly, it would not do a whole lot of damage to you if you didn't, but yeah. But I think there aren't as many quizzes this time. Okay. All right. Anything further? Okay. All right. Cover some stuff. All right. Now. Okay, so as I mentioned, this is what we're getting ourselves into. I was referred to 460 or 560 as the ultimate favorite class, this first numerical analysis class, but I think I actually like this one more because I'm all about numerical linear algebra and then numerically solving differential equations. That's all this semester is about. So, and also, I mean, by the time we get to this semester, obviously not many people go on from 460, 560 to 461, 561. So the ones who do, okay, the ones who are serious about this, in theory. Okay, so this will give you a rundown as to which parts of the book, the textbook, will be seen. But we won't be doing all of, because chapter 3 is what was called direct methods. Direct methods are, you're going to see overlap between what I'm about to cover and what you learned about in introductory linear algebra class. Here it's Math 326. Because in that class like that, you're learning how to solve system linear equations, and we're going to see that again. But it's not exactly the same because in a regular linear algebra class, you're thinking about you're doing all the work on it yourself on paper by hand. But now it's a computer who's doing the work, and that's going to affect the process some. So those are called direct methods. And then there's another kind of method that you would never learn about in a regular linear algebra class called iterative methods. Now you have seen iterative methods before. Last semester we had iterative methods for solving a single nonlinear equation. But now we're going to see iterative methods for solving systems of linear equations, nonlinear equations too. So what you learned about last semester was fixed point iteration, and Newton's method is going to play a role. And we're going to see one section of chapter 11 about how you take everything you learned last semester for solving a single nonlinear equation and generalizing it to a system of nonlinear equations. And then we get into all the chapters on ODEs, chapter 12 and 13. Okay. It just occurred to me that this semester might actually be the last time that this class runs in its current format. I'm not saying the class is going away. It's definitely not. But I've been some discussions with Dr. Schroeder and others about making this our program, the undergraduate and graduate program, taking into account the latest advances in AI, machine learning, deep learning, and so forth. And it might transform this class into, instead of just numerical analysis 2, but like numerical methods for differential equations, all about that, and then everything else in different classes. But we'll see. All this is just talk at this point. Okay, it's seems kind of weird because I've taught this class every other year since 2010, and that's a lot of times. So, how are we going to that? Okay, so what I'm going to look at for the rest of today and Monday is something you're familiar with, Gaussian elimination, but from a computer's point of view. This will be some similarity there. So the first problem we're going to consider right here is So the kind of problem that you learn about in introductory linear algebra class, where you have a system of equations, and you have, so you have n equations in n unknowns. And when you have a system of equations like that, that amounts to solving this equation, a times x is equal to b. So a is a square invertible matrix, n by n. X is your vector of unknowns. And then b is a vector of n right-hand side values. So just from an abstract point of view, solving a system of n linear equations and n unknowns amounts to solving this equation right here. And by assuming that A is invertible, we're guaranteed that there is a unique solution to this system of equations. And we know something about what that solution is, or at least we have a formula for it, x is equal to A inverse times B. The question is, how do we compute that as efficiently and accurately as possible? So when you took an introductory linear algebra class, and certainly this is true of the one taught here in the Math 326, what you probably learned to do was compute the inverse of a matrix. So you would have your you would write a matrix next to the identity matrix, and you perform all these row operations, and you transform the left side into identity, then the right side becomes the inverse. Then okay, now you have an inverse matrix, now you can just compute this and it's just going to solve. And that is a terrible thing to do in a computing environment. In fact, it's one of the cardinal sins of numerical linear algebra as opposed to linear algebra, that you never, ever, 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 ever explicitly compute the inverse of a matrix. The main reason being it's not as efficient. So we're still going to compute x equals A inverse B with some error involved, like rounding error. We're just not going to explicitly compute the inverse to do that. Okay. Now, yep, that's my point mentioned there, with the appropriate number of errors to compute the inverse. So that's one thing. So I want to touch on what are the distinctions between numerical linear algebra, when you're solving a system of linear equations, and just ordinary linear algebra, where you're doing all this kind of solving the same problem but by hand on paper. So that's one thing, is we want to carry out as few arithmetic operations as possible. But that's always the goal in numerical methods, that we want to that if three essential criteria: accuracy, of course, efficiency, and robustness or numerical stability. And that's going to be an issue for this kind of problem too. Okay. So what I'll be able to show you eventually is that if you were to count the number of arithmetic operations that it would take to solve this problem by explicitly computing the inverse and then multiplying by b, as opposed to a process that I'll show you where you perform various row operations and carry out various substitutions to compute x without computing the inverse explicitly, that computing the inverse takes roughly 4 times as many arithmetic operations. So that's the main reason to never do it. But accuracy is also an issue. So in fact, if you try that in MATLAB, MATLAB has a function called inv that you can use to get the inverse. So yeah, you can do inv of A times B, and MATLAB will give you a warning that this is not a good idea. But it's not. Okay, so that's one thing. Another thing is, okay, in a regular algebra class, you had to learn about 3 types of what are called elementary row operations. And I'm going to put you all on the spot to try to refresh my memory to what are those, if I refreshing your memory, what are those three types of row operations that they would teach you about in the class? Like,
Scaling, is that what we're talking about?
What?
Scaling?
yeah, scaling is one.
There's two more.
Don't look at me, look at Angelica.
Yeah.
I got one. There's
Okay.
two other people in here.
Yeah. In fact, that's one that accomplishes the least.
When you move it around, no, that's.
Yeah, but that is one. Yeah, interchanging rows.
Yeah.
Okay. And the one that really gets stuff done.
So I'm 2 out of 3
Yeah.
right now. Give us a hint.
Well, it's called Gaussian Elimination. So sum row operation actually helps with the elimination part. Well, I remember 2 graduate students were away in. Dang people.
Pretty good.
Adding multiple of one row to another.
See, I do that. I just want to say to be wrong.
That's everybody's problem, apparently. Yeah. Okay, yeah, and that's one that makes stuff happen. Okay, but as far as interchanging rows, when you're doing all this on paper, you wouldn't bother interchanging rows unless you needed to avoid a division by 0, like if you're systematically eliminating elements, because you're trying to, well, how I describe it in a regular algebra class is you're trying to reduce the matrix to what's called echelon form. In other words, it has an upper triangular structure. So you're trying to eliminate all these entries that are in the lower part, in the lower main diagonal. And if you're doing that as systematically as possible, like going from left to right, sometimes the process can be disrupted because you're set to divide by 0, so when you interchange rows, that gets around that problem. Now, that applies in the numerical algebra setting too, but what we're going to find out is we have a very important reason for interchanging rows that doesn't apply when you're doing this on paper when it comes to rounding error. Judicious interchanging of rows can be used to reduce the accumulation of rounding error. So at some point, I'll be able to tell you about that. Okay, and then finally, another key difference. Oh, please scroll. So those are always getting ahead of me. I was getting ahead of my notes. One thing that guides row operations when you're doing this on paper is what number to be nice. You want to try to avoid fractions and make these convenient. And the computer's like, oh, I don't care, whatever. So it's not a consideration, certainly. And the fact that chances are, in this regular algebra class, you might be scaling rows, like for instance, to make something equal to 1, or get rid of denominators, and the computer's not going to be programmed with that consideration. Okay, so similar tools that you have at your disposal, but they are used differently because the goals are different. Okay. One of the concepts that we saw at the beginning of the last semester, conditioning, is a problem well conditioned or ill conditioned. We saw that numerical differentiation is ill conditioned, numerical integration is well conditioned. Solving a nonlinear equation could be either one, depending on the function you're finding the root of. So we're going to have a specific expression for the condition number for solving ax equals b that we'll get to later. So the goal here is that if we have any n by n invertible matrix A, and then the right hand side values b, that we end up having an algorithm for solving A equals B in that situation. So what I'm going to take you through in these opening sections is the design of such an algorithm that takes into account all the criteria that we want to meet, accuracy, efficiency, robustness. Now, the algorithm that we end up with may not be as effective if a problem is ill-conditioned. And unfortunately, there's not a whole lot we can do about that because a problem being well-conditioned or ill-conditioned, that's about the problem, not the algorithm. So if you're fed that problem, whatever method you throw at it is going to have some difficulty, but we can help the situation to some extent. So what do? So this is a mindset that we should always use when trying to design an algorithm to work across a broad category of problems, like in this case, all square invertible matrices. So you ask yourself these two questions. First, when is the problem easily solved? There are certain cases where you know exactly what you need to do. Like in the case of numerical integration, the easy case was if you're integrating f of x to a polynomial, because that's the easiest function to integrate. So you take care of that first. And then, for problems in general, is there a way to reduce it to the easy case? So for example, back to the numerical integration case, you get a general non-polynomial f of x, you approximate it by a polynomial, by interpolation, and then you integrate that. So here too, we're going to see there are certain matrices for which solving a system of equations is particularly easy. And then once we have a general n by n matrix, how do we take advantage of a knowledge of an easy case? Can we transform a problem into an easy case? Yeah. And so every time we have something, an algorithm design, this is a mindset to use. What we're going to look at first is when can you solve a system easily? The easiest kind of all is where all of the equations can be solved independently of one another because each one of these n equations involves a different unknown. So for example, here we have this equation, the first one only involves x1. The second one only involves x2 and so forth. So if all the equations are like that, then you can just perform n divisions, and, assuming all of these entries of A, A1, 1, H2, etc., assuming they're all non-zero. Otherwise, the matrix would not be invertible. And then you're done. So in this case, we call this a diagonal system because the matrix of such a system is entirely zero except along the main diagonals where you can have your non-zero entries. So, everything, when I have blank space in the matrix, everything but that's assumed to be zero. So everything down here and up here is zero. So when you have a diagonal matrix, that's the easiest case. And you're only performing n floating point operations, just n divisions. So in a regular algebra class, when you would go one step further beyond echelon form, I think it's called reduced echelon form, where it's zero not only down here but up here. So then the system is trivial to solve once you get to that point. All right. But there's systems that are not this simple, but still fairly simple to solve. Because here we had each one of the equations depending on only one unknown. But we can proceed pretty easily even if we don't have that. So a situation like this system right here, the last system, the last equation in the system only depends on one unknown. So anytime you have any of the equations involving only one unknown, that's the trivial case. You just divide and you're done. So we can't do it with multi-equations, but we can do it with x3, the last unknown. Now you know what x3 is. So then you can substitute it into the second equation and do a little bit of algebra, and now you can get x2. Now you have x2 and x3, substitute both of those up here, and then you can quickly get x1. So they're just cascades. So in this situation, where the last equation depends on only one unknown, and then each equation above it introduces only one additional unknown, then you have the matrix being what's called upper triangular, because everything below the main diagonal is zero. So this is what's referred, what you would know of in a regular algebra class as echelon form. If you can get the transform your system to have this form. So in this case, you can do what's called back substitution, because you're going backwards through the equations that you performance division. So this is what I described earlier. You substitute x3 into this equation, and now this is your formula for x2. Then you substitute your x2 and x3 values in the first equation. So now you have this formula for x1 in terms of x2 and x3. So each unknown takes more work to obtain. So x3 was a simple division, x2 was a little bit of work in the numerator, and then division, and x1 we have more terms in the numerator as you go. So whereas solving a diagonal system took n operations, back substitution requires n squared. That's a byproduct of having to do more work with each unknown.
What required in? I didn't hear you.
Oh, okay, so this diagonal case, we only had to perform n operations.
Oh, okay.
But the other triangular case is n squared. And then finally, lower triangular system that's essentially the same as the upper triangular case. Okay, so it's like this case flips. So all entries above the main diagonal are zero. So in that case, it's everything's in reverse. The first equation depends on only one unknown, so you can solve for it immediately. Substitute that in the second equation. So you're going through equations in order. So we'll see more about forward substitution later. We don't need to really deal too much with it now. But like back substitution, again, n squared operations is what is needed. So those are the three simplest cases. So they all stem from having some equations depend on only one unknown, so you can immediately solve it, and then another equation that depends on only two, only three, etc. So you can just keep substituting. That leads to these processes of forward and back substitution. So now the goal is to handle a general square vertical matrix. If the matrix does not have this kind of structure, it's not triangular, it's not diagonal, what can you do? Now, where's my further? Because these notes are meant to they're meant for not just today, but also Monday. I was thinking about what I want to distribute among the 2 days. Okay. All right. Okay. Now, so as you know from a ordinary linear algebra class, what you can do to get a general squared verbal matrix to some kind of triangular form, or as was called in a class like that, row echelon form. You have these three types of row operations at your disposal. So the idea is you want to be able to, so given a general square invertible matrix, how can you use these row operations to get the matrix to upper triangular form? Because if we get upper triangular form, we know what to do at that point. We can just use back substitution and finish the job. Okay. Now, so I want to focus on this last operation right here. So you're adding or subtracting the multiple of one row from another. So what I'm going to discuss here is the elimination of a single entry. So you have some entry in your matrix, you want it to be 0, how are you going to make it 0? So let's suppose that this entry, aij, for some I and j, is what I want to get rid of. Now, I'm going to assume that I is greater than j. Now, actually, I'm going to put this in the notes. So one thing to know about matrices that are upper or lower triangular is what does that mean for individual entries aij? A is upper triangular if aij is equal to 0 whenever I is greater than j. So the row index is greater than the column index. Those are the entries that put you in the lower triangle. Similarly, A is lower triangular if aij is 0 or I strictly less than j. I found it very helpful to keep these inequalities in mind. That if I'm dealing with a matrix entry in a lower triangle, that's row index greater than column index, and so on. It's one of those good to know things. And finally, A is diagonal if aij is non-zero, only when I is equal to j. So I equal j puts you in the main diagonal, I greater than j is below it, I less than j is above it. So if I want all entries, if I want upper triangular, this is what I want. Ij is 0 if I is greater than j. So that's why I have this assumption right here. That I'm trying to eliminate such an entry. I'm going to assume that I is greater than j. So the idea is, if I go back and look at an example that I had earlier of an upper triangular matrix, this one right here. If I'm in this row, for example, the second row, and I wanted to eliminate this entry, the rows above it have more non-zero entries. So rows above where you are have more non-zero entries in them, and that's what you can use to perform elimination. Okay. So the idea is I'm going to take eliminate aij by choosing some row above row I. So that's row j. And I'm going to take a multiple of row j and subtract it from row I to make this entry 0. Now, in terms of what happens to the entries, what does that look like? It's this equation right here. So the idea is I'm working on row I. Now, if you take another row, row j, and I multiply it by something, and I subtract that from row I, every entry in row I is going to be affected. That's what this equation is saying. That for every single column k, so notice k goes from 1 to n. So across all columns, row I is equal to itself minus some scaling factor that I'm calling a multiplier. I haven't said what it is yet, but I'm about to. Times row j. So notice the column index is the same. So the entry in row k of column I has subtracted from it the scaling factor times this entry that's in the same column, but row j. So that's what a row operation looks like, entry by entry. So if you're coding up a row operation in MATLAB, this is the kind of statement that you would use. It's converting to MATLAB syntax. So if I let k range from 1 to n, then like in MATLAB, I would have a for loop, k going from 1 to n. That row I is equal to row I minus multiplier times row j. So, yes?
I have a silly question. I think it's silly. So like in the matrix, right?
Yeah.
I think I'm confused on what exactly I and J are in the like rows. Right?
Okay. So right now, I and j are arbitrary.
Uh-huh.
I'm just talking about a generic elimination operation. The only assumption we're making is that I is greater than j.
Okay, just it has to be above it.
Yeah, because the only entries we want to eliminate are the ones in that lower triangle.
Okay, that makes sense.
Yeah. Now, as far as right now, I'm talking only about a single row operation, and then we're going to figure out how to do all the row operations, and we'll cover that later. Okay. So, if I carry out a row operation like this, I need to make sure that the effect of this row operation is that aij is equal to 0. So, if I go through this equation, remember k, the column index k ranges over everything from 1 to n. But if I look at specifically what's happening in column j, that means I'm setting k equals j throughout this equation. And that would give me this. So all I've done here is replace k with j. So in other words, the entry I want to eliminate is going to be equal to itself minus my as yet unknown multiplier times the diagonal entry in row j, column j. And I want that to be equal to 0. By setting it equal to 0, I now can solve this equation for my multiplier. So if I set my multiplier equal to the very entry I want to eliminate, divided by the diagonal entry in the same column, column j, that is the multiplier I need to cause this updated entry to become 0. So that's how a single row operation that's targeting a single entry in the lower triangle matrix has to run. That we have to choose a multiplier in this manner. Okay. Now, okay. I think, oops. Tell us about the research account. Should be my folder for this class. Okay. All right, so what I'm going to do is I'm going to create a random matrix. I'll need a diagram for this. Okay. And now, okay, so here's my matrix. I've never had MATLAB create a random matrix that somehow turned out to not be invertible. The event is very unlikely to happen, but I'll make sure. I'll take its determinant, which needs to be non-zero for invertibility. Yes, it is invertible. Okay. Now, so all these entries, like these four here, these bottom three here, bottom two, and the bottom one, I want those to be zero. So, but I have to think about how all these, I now know how to do a single elimination operation, but what was the order in which they are carried out? So I'll give you an example. You can do something that's actually kind of foolish, but it gets the idea across. So first we're going to eliminate, I'll just pick an entry here, say the entry in row 3, column 2. So in other words, I is equal to 3, j is equal to 2, what I described in the notes. So I'll make my multiplier. So m32 is equal to a32, the entry I want to eliminate, divided by the diagonal entry in the same column. So this is the formula for multiplier I gave you earlier. Okay. And now I'm going to perform the actual row operation. I'm going to take row 3. So remember the notation here. First index is a row, second index is a column. By saying colon, I mean all columns. So this refers to the entire third row is equal to itself minus the multiplier times the second row. And let's see what that does to the matrix. Sure enough, that entry is 0. Progress. But now I have to realize, oh wait, I want to eliminate that entry too. So I'm going to so I go through the same process. I'll limit to free 1 entry, and then I'll use the diagonal entry in column 1 instead. And then the row operation will be almost row 3, but now I want the multiplier, this multiplier times row 1, okay? And, okay, that entry is made 0, and this is non-zero again. I stepped on my own toes. You have to think about the order in which these operations are applied. So if I have my original matrix, that's a full matrix, and I need to eliminate all the entries below the diagonal, in what order should I proceed to not have a situation like this happen, where I end up undoing work that I'd previously done?
Starting with the first one that you want to eliminate? Or
Um,
all the way to the left?
yes, all the way to the left. Go from left to right. So, okay, so now if I'm going to restore my original, okay,
I'm killing it today.
yes, you are. Okay, so for example, if I were to, go with first column. Okay, so m21 is equal to a21 divided by a 1, 1. Okay. And then I do second row equal to itself minus first row. Okay, that's done. And then I do the same for the entry right below it. So row 3, column 1. Row 3. Okay, and then I could continue, like getting rid of this entry and this entry, but I'm gonna not think about those right now. Now I do want to eliminate this entry, row 3, column 2, like before. So if I do the same kind of thing, where I
What button is it to hit back?
sorry, what?
What was the button to make it go back again? To like do what you brought up above?
Oh, the arrow keys. Yeah, like use up arrow and down arrow to scroll for your commands.
Okay.
Okay, so I set the multiplier for targeting this entry, and then I use the second row. Okay, and there, I've not stepped on my previous work, and the reason why is when I'm at this point, to eliminate this entry, I want to take row 2, multiply it by something, and subtract from row 3. So in other words, third row is a linear combination of itself and the second row. But because this entry has already been made 0, the row operation won't have any effect on this entry. That's the key, is that when you're working on a certain column, okay. So in general, whoops. All right. When eliminating Aij in this manner, what we need is these entries that are in row J. Row J, column K to be equal to 0 for K less than J. So that's what happened in the case that we were just looking at in MATLAB. I was equal to 3 and J is equal to 2. So I needed A 2, 1 to be equal to 0. And it is. So everything works out just fine. Okay. So what you can do is in column 1 and column 2. So as long as you do that, then you're not going to have a problem. Okay. So this now we're beginning with algebra. if this is a LaTeX thing, I'm about to type in some pseudocode, and I want the indentation to work out right. Because, so if we start, looping, iterating over columns. So J's going to go from 1 to n. Although, if I look at the example again, here's a 5 by 5 matrix. So I need to eliminate the bottom 4 entries in column 1, bottom 3 entries in column 2, bottom 2 entries here, last entry here. In column 5, I don't need to do anything, because that doesn't affect upper triangularity. So really all I need to do is I can go up to n minus 1. Because there's nothing to eliminate in column n. So then what I can do is should be lowercase j. Eliminate, I shouldn't work precise here. Sub-diagonal entries below the main diagonal in column J. Well, which entries are those? So that would be, if I use I as a row index, so I would start below the diagonal, so I starts at j plus 1, and I keep going all the way down to the bottom. That's row n. Okay. So what I can do is at this point, inside this loop, I can eliminate just the entry, a single entry aij. Using row operation. But that's this row operation that I described here. Okay, now I'm almost out of time. Okay. So to go through an entire row, I have to iterate over all the columns to handle each entry in that row. So we need the index k for that. Now, the way this row operation was described, k goes from 1 to n. So if I fill that in, okay, and then I can and I can put in the equation I had before, aik is equal to itself. I need the multiplier, don't forget that. Okay. Okay, so for each row operation, I need a multiplier. I'll put that in. I know. Okay. All right. So this will carry out. Now, but the thing is, what have I just said? Ajk is equal to 0 for k less than j. So if this entry is already 0, then this line won't have any effect. So I don't need to carry this out for k less than j. So I can start here. Okay, going from j to n to save myself some work. The y operator is something that's going to be 0. But so if I run this will reduce the matrix to upper triangular form. So we have a Gaussian elimination algorithm. But I can actually do a little better than this. I don't even need to do column J. Because what is AIJ specifically supposed to be? After doing all this, what is supposed to happen to AIJ?
0.
Yeah, if we already know it's going to be 0, then why carry out the arithmetic for a result that we already know? So in a practical implementation, we actually start here. Okay, going from J plus 1. So we do need to update the rest of the row so that subsequent row operations will be correct. And this is what students are always thrown off on every time I teach this topic. And they think, oh, the loops are starting with J because they implement this, like in a homework problem, and try it out in matrix. Like, well, matrix is not over triangular. No, but what is in the upper triangle is what it's supposed to be. And that is what matters. That is what makes sure that what are you going to do to solve the system? Because don't forget what we're trying to do here. We're trying to solve a system of equations. Nothing else matters. Having a nice, pretty upper triangular matrix, visually appealing, and does not help us solve a problem. So we don't do it. Okay, so I'm just trying to head that off before you guys start working on these things. It's all about reducing the operation. Never waste an operation. Because we could perform a billion other menus. Okay, well I definitely have stuff. That's a good starting point. So seeing this on Monday.